Thank you all for joining us today. We're excited about this webinar with Patrick. He's going to do a great job. I'll start by introducing myself. I'm John McNamara. I'm a technical sales engineer here for Sodic Injection Molding, and I cover a few key areas of the country that are focused on medical device manufacturing. And we're excited to have Patrick here today to support our Sodic and Friends webinar series. Patrick is a R&D engineer for MTD Micro Molding. He graduated with a plastics engineering degree from Penn State, where he specialized in research and development. He works closely with internal and external experts in the polymer science and med device space. At MTD, he delves into intricate polymer phenomena prevalent in micromedical processing, and he's an invaluable asset in the advancement of micromolding technology. MTD Micro Molding, we're excited to have them be a part of this as well, and they've been a great partner and customer of ours for a long time now. They're a US-based leader in micromolding for medical and health tech industries. They're a single source partner specializing in bioabsorbables, drug delivery systems, and advanced overmolding processes. They're focused exclusively on medical applications, and they accelerate development and ensure precision for the most complex designs backed by ISO certifications, FDA registration, and ISO Class 8 clean rooms. Before getting started here with this presentation from Patrick, I just want to kind of go over a little bit of how this will work. So Patrick will give his presentation for about 40-45 minutes. Once he's done, we'll go into a 15-20 minute, potentially longer, depending how it goes, Q&A portion. So during the presentation, instead of interrupting and asking Patrick questions while he's presenting, we'll have you click the Q&A tab at the top of your screen and submit your questions there. I will be able to see those, and Patrick will be able to see those, and we will go through those at the end of the presentation. So with that said, I'll hand it over to Patrick, and we're excited to learn a little bit from you today.
Great. Oh, thanks for that.
Yeah, thank you, Patrick. Thank you, John.
Oh, yeah, thank you. So thanks for that introduction, guys. So today we're going to talk about something that is pretty interesting, and I think is not addressed as much as maybe it should be. But it's certainly not addressed as much as some other facets of injection molding and manufacturing, and obviously that is handling of micro parts and ejection. So I feel like most of the time, if you go to a seminar, everything's heavily front loaded, meaning design, mold making, and processing, or heavily backloaded, like inspection and packaging and things like that. And there's kind of this little void in the middle where, some people don't tend to talk about. It's not that we don't think about it, but we don't tend to talk so much about what happens to these parts in transit from the molding press to, the shipping truck or the air freighter or whatever. And that's what we're going to talk about today. And this is particularly important in micro molding because of all the reasons that we'll go over. So before we get too much in the weeds here, and just to elaborate a little bit more on where we are and who we are and what we do, like we already said, MTD Micro Molding, we're 100% medical right now. We're 100% micro, and we're located in central Massachusetts. And I think we've been around now for about, I want to say it's about 54, 55 years. And we do a lot of stuff here. We are primarily a contract manufacturer, but we do have our own machine shop. We do have our own metrology. We do have a lot of our own automation things, and we do a lot of, I guess you could call it, consulting for our customers up front too. So in other words, engineers like myself might get involved with a new potential customer before your drawing's even finalized, right? Because that kind of granularity with how we're going to sort everything out ends up being really important with micro molding. So this is where we are, and that's kind of what we do. So we have 5 right now, ISO Class 8 clean rooms, and I think we're up to 18 molding cells that are all Sodic presses. So we run exclusively 20-ton Sodics here at MTD. Most of them are horizontals, but we do have some verticals as well that are also 20 tons. And the verticals, most of them are rotary platens, all but one. And we use those for hand loading and overmolded jobs. So we do have that capability at MTD. We do it quite a bit, as well as fully automated horizontal cells. And then it's worth mentioning, and we'll talk about it a little bit more as we move on here, but every molding cell has its own automation cell as well. So most of the time we're running 3-axis robots, but we do have a 6-axis as well that is extremely important for reasons we'll talk about. But that's kind of our floor, and this is a picture of one of our cells in one of our clean rooms. So Sodic plays a big part on why we are successful in what we do. The next thing I want to cover is, what do I mean by micro? Because this definition is different for everybody that really talks about it. For some people, micro means a bottle cap or something along those lines, but for us, we mean something much smaller. So much so that we have to kind of redefine what's possible a lot of the time. So this little kind of bracket on the screen here with wall thicknesses is part of a publication we have on our website, talking about what's possible with thinness, what thin features are possible with what materials, right? And as you can see, so things like polypropylene and LCP, we can pretty much consistently fill 2000s wall features with no problem, right? So typically, kind of maybe too simply, a lot of the time we define micro as a 1-inch by 1-inch cube, but we are known to go outside of that kind of 3D space as well. And our features can even get smaller than a thousandths. Like, for example, the radii here, this is we would call that 2/10 or 2/10,000ths of an inch, right? So this is all capability that we have here with molds and tools that we build in-house. So to kind of put that into perspective, in a real life perspective here, this is a screenshot from our portfolio on our website, kind of depicting the size of the parts that we make. And as you can see, a lot of these are depicted on coins right now and are quite small. So one thing I want to point out with this is, when we get to this size, there's a lot of things that would otherwise be almost negligible or intuitive that you wouldn't have to worry about, that you all of a sudden might have a huge problem with if it's micro. For example, with a part this size here, this blue piece, what happens if we wanted to put a cavity ID on that, or even any of these, really? We'd have to ask the question, what's the depth of a laser engraver? And is it going to be 50% of the wall thickness or 25% of the wall thickness? And is that going to be an issue for your application, right? Or another question might be, if we have a core pin here that is going to generate an internal ID for your device, what is the size of that core pin, and does it have the integrity to withstand injection pressures so that it doesn't break or deflect, right? You might not be able to mold a wall at all because the core pin just gets pushed around too much. So these are some examples, and I know those aren't part handling examples, but these are some examples of the attention to detail that we need to apply to everything that we do in micro through the entire process, right? So a lot of the times when I'm working with new employees that come to MTD, I find myself saying this, is that we need to have an exceptional attention to detail. And I think initially what that means for whoever receives that, right, is, okay, I need to have, they apply it to the most obvious place to apply that to. So if you're a processor, you go, okay, I'm going to have the mold open, I'll take the part out, and then I'm looking at it under a microscope, and I'm going to scrutinize that part as best that I can. Right. And that's the attention to detail that we're referring to. Or if you're a mold maker, you want to make sure that, your drop indicator and everything that you're about to measure is exceptionally level before you measure it. That's your attention to detail. And although all those things are true, this attention to detail and this concept of it kind of evolves into a lot more than that, right? Like, what happens if we end up having static in our molding cells being a large issue, right? We can't just have static because a part of the mold might open and a part might just flip and go upwards instead of downwards, or side to side, or behind a mold component or something like that. So we need to have all these anticipatory details, and all this attentiveness to make sure that we can first and foremost manufacture this part, but then also how are we going to ensure that that part gets to the customer in good shape, right? And in functioning shape, right? So we have this responsibility to this attention to detail, that we really need to recognize and shoulder that responsibility in order to be successful. And I would urge to kind of expand that concept to everybody involved in a micro program, right? That includes the customer, the OEM, or any vendors, or of course the manufacturer themselves, right? Is that early decisions impact, yes, cost, but also complexity. And what I mean by complexity is the complexity of the whole program, including how are we going to handle these things? How are we going to demold these things, right? And there's some categories that might not be so intuitive to part handling, right? Like, for example, I want to jump through some of these chapters here that kind of take you on a ride and implore you to think about the decisions that you would make, what you would originally think about when we're talking about these categories. And then we might explore some other ways on how things can get more complex as we get through the process, right? So the first category would be material selection. Okay, so I think for a lot of customers or part designers or inventors, of course, as it should be, your primary concern with material selection for your device is the demands of your application, right? Do I need certain mechanical properties? Do I need certain chemical resistance properties? Do I need certain thermal resistance properties? All these things, right? And those are all appropriate. And then maybe the second depth category of that would be, is it processable? What temps is it going to be exposed to in manufacturing? These kinds of things, right? But then there's also other types of concerns that we might have, like, is the material polar or non-polar? And how is that going to interact with ambient static around other things, other devices, other cells that material has to interface with, right? Is the material rigid or flexible, things like that, and how is that going to impact part handling down the road? There are a lot of these not so obvious questions that you might ask yourself that, if you consider the whole thing and really look at it, affects how we're going to have to transport these things around even the room, right? So at MTD, one major thing that I do is I help our customers with their material selection if they need it or if they want it, right? And material selection is a conversation that we could talk for an hour about alone, and we're not going to do that. But in short, what I can distill all this down to is that there are a lot of different materials that are very, very different. But what it all boils down to is the chemistry, right? The material's chemistry and its morphology is going to drive that material's behavior, right? So for example, polycarbonate is an amorphous material that's going to be tougher, right, and more flexible, but also more polar, right? And polypropylene is another example of something that's not so polar, and is crystalline, so it has better chemical resistance than polycarbonate does. There's all these things, right? But the two things that I want to hone in on in particular here with part handling is rigidity and shrinkage, right? If something shrinks onto a core pin, for example, and it's very soft, how are we going to get that off the core pin? How are we going to strip that off the core pin without damaging the part, right? Or if something's very rigid, depending on how thin the parts are, that rigidity might turn into just brittleness, because there's not enough material or wall stock to present any kind of real strength, right? So these are choices that will absolutely affect how delicate the parts can be post molding. And again, we'll get into some of that as we get further into the presentation, but I want to implore you to keep these types of things in mind, and pretty much never assume that you've thought of everything when you're just starting off. with your device, right? Or even if you're consulting with a customer on what material might be appropriate for the program, right? Another thing I want to highlight is durometers, right? So this is a major thing too that can totally change the scenario of a program, right? So something like PBACs or PBA, or TPUs and TPEs, things with hard blocks and soft blocks in the polymer chain, drastically change the material behavior too, right? So if we have a sharp edge and we blunt that sharp edge, is it going to recover or not, right? And you might have one grade of a TPU or something that behaves just fine, but then you might have another grade that reacts to static completely different, or shrinks onto a steel component completely different. And then demolding and part removal of that material completely changes depending on maybe a 40 shore D to a 70 shore D, right? The next category with this is, and this is a big one, is part design, right? And there's a lot of things that we could talk about with part design as well. You know, for example, in this piece here, like if this is a hollow piece, right, or it has an internal ID, is that core pin going, is it going to shrink onto the core pin like I already mentioned? And what kind of ejection strategies can we look at for that? Those are things that are somewhat common when we think about part design, but two things that I want to hone in on with part design in these examples is gate location and how that can actually affect your part orientation in the mold. Because gate location, believe it or not, actually dictates almost the entire way the mold is constructed to begin with, right? And it also dictates the appropriate ejection surfaces that you're going to have available to you during ejection itself, right? And then that's the other thing, is that I want to talk about restricting ejection surfaces due to application, and some things that we can do to get around that. But to brainstorm initially, I have this little widget here, right? And I want to create a little bit of a scenario on how we may or may not handle this, right? So in this example, we have somewhat of a little barb staple type device. And in the scenario I want to paint here, these barbs are too small to get any conventional ejection on, right? So there's no way for us to get a pin in here that's going to have any kind of integrity or have any kind of real land to push against on the part. So ejecting on these barbs by themselves is pretty much impossible with a micro part, right? Also in this scenario, down here on this kind of crossbar where my cursor is, we are unable to have any witness lines at all. That means, you know, no ejector pin marks or anything like that. So, you know, in this hypothetical scenario, the would-be customer has barred this area from having any witness lines, and due to the part size, these features are too small to get any conventional ejection onto. In addition to that, if we take a closer look, this sidewall here is straight, and this wall has a radius on it. So this sidewall is actually taking away from the overall projected area wall width, right? Which is ultimately going to minimize the size pin that we can get into these areas too. So given this scenario, all we have are these thin kind of posts that we can get ejector pins into, and those ejector pins are going to be exceptionally small. So the concern here would be, are these sharp barbs going to stick into the steel, right? And if we can only push in these areas, then will it lift out of the mold evenly? And if not, then we might get some torque on this barb, and the part overall might fail, say, a flatness spec or a straightness spec or something like that. So, you know, this is something that we take a part that is relatively, you know, simple to fill, right? And all of a sudden the mold construction is complex, and it has everything to do with how the demolding process is going to work, right? So obviously in this picture here, we would gate in the center of the horizontal post to get even flow down both barbs at the same time, not to overpack any side, right? So this is, I think we can probably, hopefully all agree that this is a good gating location, right? So in this scenario, how would we solve this problem? This is a perfect example of when two-stage ejection would be appropriate, right? So in this case, why not take the entire footprint of the cavity and have that all lift out for as far as it can, right? And then we can also include this horizontal bar area now, because having two-stage ejector bars instead of ejector pins eliminates any possibility of witness lines in that area, right? And then as we extend off, we'll put a ejector pin on the runner itself, where the material has a little bit more integrity, make sure that the gate lifts out of the steel evenly as well as the part, and then utilize half the footprint of the entire part to make sure that those sharp barbs also lift out, right? Because if we were to just eject like this on the left and then get some automation to pick this part out, we may still run into the risk of these sharp barbs sticking into the steel, right? Because those are separate steel components that are necessary to make that sharp edge. Okay, so we'll two-stage eject so that we can lift these barbs out safely, and then we'll present the part into a place where we can lift it consistently. Okay, so in this next scenario, I have, again, it's just kind of a geometric widget here of a rectangle. And if we were to imagine just molding this part all by itself, I think it would be relatively straightforward, right? We could say, maybe we could say we'll put a tab gate here. And then the mold pull direction, I understand this is kind of an ISO view of the part, but I think that you can kind of get what I'm getting at here. The mold pull direction would be up and down, north and south of the page here. So we'll tab gate here and then have a simple core here to create the internal geometry, and it should be an open and shut tool, no problem, right? But let's say for some reason due to application, we can't gate on this edge, right? And we can't flow down this long edge, and they don't want any blemishes. Actually, they don't want any blemishes anywhere except for this bottom surface, right? They say that's okay. So all of a sudden, now we have to lay the part down because the mold pull direction or the mold opening direction is the same way, okay? So maybe we could still tab gate it then, that's okay. We could tab gate maybe in the center and split the flow and still avoid weld lines and all those good things. The only difference here is that now that this internal geometry is undercut, we'll have to side action it, right? So the mold demolding is a little bit more complicated now because there's still staged steel that has to move before the mold can completely open. But it's not necessarily the end of the world. However, if we make it into a micro part, everything still changes. You might ask yourself, is edge gating still possible, right? So now that we've put some dimensions on this thing, these walls are only 30 thousandths of an inch thick, right? So is this wall, right? And this whole rectangle here is only 140 thousandths of an inch wide, right? I think I didn't dimension this part, but this whole length is about 100 or so. So now if we put an edge gate onto this part, we have two things that we have to deal with. We have to deal with degating the part somehow, right? Which means post handling the part when it's so small, right? That means interfacing with the part an additional time. And then we also have to deal, and this is probably the most important one, we have to deal with gate vestige, right? Or damage to the part. So with a part this small, to get an effective tab gate in there, the tab gate is going to be maybe the size of the whole part or it might be 50% of the base of that part, right? And the gate vestige alone might deform that entire wall. So if degating the part is going to destroy the part, then what's the point in even trying at all, right? So the question is, how would we approach something like this? And in a scenario like this, I don't think we would actually edge gate something even this simple. In this example, we would suggest something like this. So the mold pull direction, again, is in the same direction, north and south. And I think it would be much wiser to think about tunnel gating this into that surface instead. So in these pictures, this green insert here is a side action, right? And that's the slide that's creating most of that internal geometry. Now this gray piece would be the ejector bar. So no ejector pins because the part's too small now, but we could lift it all with a whole bar, right? And the reason why this is particularly strategic is because on the right here, once this side action moves and retracts out of the way, because part of this geometry is buried in steel, and also because this runner system is subterranean, we can count on this part staying in the cavity, right? So if the runner wasn't subterranean and this feature wasn't buried in the ejector bar, there wouldn't be a whole lot that would guarantee that this part would stay in the cavity once this retracts, right? Because the gate's so small and static might influence the part. So as this steel moves away, it might pull that part off the gate with it, right? And then it could go wherever it wanted if static was a problem, say. So by burying a feature into the ejector bar and then making the runner system subterranean, we give enough influence for the part to stay in the part cavity while the side action can get out of the way, right? And then there's an additional kind of pro to this approach, and this is kind of a more obvious one, but when the ejector bar advances, now we don't have to worry about degating the part later, right? Because if we did have to worry about degating the part, that would mean that we would have to build some kind of fixture to interface with the custom runner and part. And then we would have to, that fixture would have to have a certain amount of precision to make sure that it cut the gate clean, that it prevented any, say, vestige or dragging or pulling of the wall. And it would all have to be automated and destaticized and all these things. It's just another approach where now that we auto degate the part, we can pick both the runner and the part away with automation, and then just disregard the runner system and then manipulate that part after it's been degated, right? So any way that we can minimize interaction with the part is good, because that means that there's less risk to damaging or even losing these parts, right? Sometimes if you drop a micro part on the ground, you can't even see it, so it's gone forever type of thing, right? So now that our parts are out of the mold, what happens next, right? Oh, I'm sorry, I still have some ejector pin slides. I forgot about these ones. So before we move on to automation and what happens with the part after it leaves the mold, I want to talk a little bit more about how ejector pins can get influenced by wall thicknesses, and how material selection choices can also influence the ejection scenario of your part, right? So in this little example, we're just molding something, say a picture frame, right? But the picture frame is very small. So I have 30 thousandths part width. I have about a 12 thousandths wall thickness and say a 6 thousandths gate, right? So if we gate here, obviously the part will flow left to right and then weld here, right? And in a scenario where you'd want rigidity in this part, right, you might pick, let's say you pick PEEK for your material, because PEEK is extremely strong. At a wall thickness of only 12, this weld line is going to be particularly weak. Not just because the part is 12 thousandths in and of itself, right? So for reference, a human hair is about 3 or 4 thousandths in diameter, right? So at wall thicknesses that thin, the part will just inherently be more weak, right? So that's like kind of what I said earlier, where material rigidity can actually translate to material brittleness when we get to wall thicknesses and features this small. But also another thing to highlight here is, because the wall thickness is so small, the melt flow front is not going to be able to stay warm for very long. That means you're going to have very rapid cooling rates, which means it's going to be even more difficult to pack out and optimize this weld line strength when the melt is cooling so rapidly, right? So the risk that we might run here if we put, say, ejector pins on these corners is that when we push the part out of the cavity, if there's any unevenness at all, we might put a little bit of torque on that part, and it might not take very much to break a weld line like that, even in a material like PEEK, right? So when we get to the micro level, when it comes to demolding, if this was an actual picture frame, we could probably just lift that out with pins, no problem. But in a scenario like this, we're going to be limited to maybe a 20 or 25 thousandths ejector pin diameter, which is going to exert a lot of force on its surface area. And we might break the part. So in a geometry as simple as this, we might have to resort to making the entire floor an ejector to ensure that this lifts properly and it doesn't put any unneeded torque on the weak areas. And then that could add, obviously, mold complexity, but also processing complexity, because we want to process and ensure that we don't get stovepipe flashing down, the entire edge of the part. So I wanted to highlight how, again, your material selection choices and your geometry and gating choices can absolutely manipulate how these parts are demolded just based off of them being micro alone, right? And a little factoid for you here: generally, ejector pin sizes don't go below 10 thousandths of an inch. They're not typically regularly supplied like that. So if you had features that were, say, under 10 thousandths width, and you wanted to get an ejector pin in there below 10 thousandths, you'd probably have to get that wire turned or something like that. And the last thing I want to talk about with mold components is core pins. Core pins are another one of these kind of categories that isn't necessarily intuitive to how it can manipulate demolding a part. So in micro molding, core pins can be so small that they can be very difficult to control the temperature of, right? Particularly once the mold gets up to operating temperature, those tiny core pins can be very hard to cool down, right? In the macro world, if you had a core pin that was maybe an inch or so in diameter, it would be relatively easy to get a bubbler in there and hook it up to its own cooling circuit, right? And cool the core pin that way. But in micro molding, it's not really possible. You can get bubblers that are that small, and you can do the construction the same, but the GPM, the flow rate of the coolant through the pin just isn't going to adequately cool it. It can't keep up with the introduction of hot plastic over and over again, right? So the reason why this is important for demolding is because if we look at a part that, say, has a low TG, glass transition temperature, a low softening point, or we look at a part that just has low durometer in general, if we were to get maybe stripper ejector on there, that might kind of accordion the part trying to get it off the core pin because the core pin's hot, and we can't keep the wall integrity intact stripping it off the pin like that. Or another scenario might just be that the shrinkage is too high and a part hugs the core pin so tightly that pushing it off with a stripper ring might damage the part that way as well. So one way that we can get around this to demold it properly is to change the core pin material to something with a more efficient thermal conductivity value, right? So a couple that come to mind right now would be, say, carbide or beryllium copper, so that we can remove the heat through like convection and conduction, normally without having to put a cooling circuit in there. Now, if we do that, say with beryllium copper, we might kind of mess with the biocompatibility of the medical device, right? So in order to get around that, we might look at some plating options, so that we can get the surface interaction of the metal component with the molded plastic to be biocompatible again. Now, on that topic, another kind of pro or advantage to plating can be sometimes that can help release the plastic off of the steel too during ejection, right? So if something does have high shrink, maybe we can look at certain plating options or even polishing the steel to help release that plastic off of the core pin if it's heavily shrinkage on there or something. Another little factoid and a caveat to keep in mind here, though, is that if we do plate micro steel components, those components have to actually be large enough to accept the plating, right? So if you think back to my previous part example that looks like a rectangle, if we were to plate that, we would increase the radii of the corners because the plating itself has a certain thickness to it as well, right? And depending on how small your micro part is, that plating thickness might actually increase your wall thickness by 50% or 100% or whatever it might be. So that would influence your part geometry as well. So you have to be careful about that if you're going to explore options like this. Okay, so now I want to talk about a little bit about some techniques and what happens to the part after it leaves the molding cell. After it leaves the molding cell, but before it gets packaged and shipped. How do we ensure that the parts stay the way that they should be, or the way that they were once they get out of the mold? This is something that covers a lot of different categories, but again, there's this attention to detail necessity that we have in micromolding that has to cover this kind of activity. So the first thing I want to talk about, or think about anyway, is the end of arm tooling. So at MTD, we have like I said, we have our own custom tool shop where we make all the molds in-house. But that's not all we make. We make just about anything we need to make back there. And this includes end of arm tooling. So for those that don't know, what I mean by that is these are the custom tools that go on the end of the automation robots and effectively interface with the parting line of the mold to extract the part, right? So in this scenario, a lot of the time that, we'll make the bulk of these end of arm tools out of aluminum, but sometimes, if we have a part that has an ultra small wall thickness, again, let's use a peak example where if it's too small, gripping it with pneumatic aluminum grippers might actually damage the part, even though it is a high performance material. So we might explore custom machining some pneumatic gripper out of maybe Delrin or nylon, or maybe sometimes even PEEK, so that it's not getting clasped with a material that has such a higher rigidity than the plastic itself, right? Another thing I want to point out here too is that here you can kind of see this is probably a scenario that was a tunnel gate like I talked about earlier, right? And you can kind of get an idea as to how clean these tunnel gates can shear off the runner system, right? And that has to do with the mold construction, but it also has to do with your material selection, right? So if you have a very highly ductile material, shearing this gate off, whether it happens in the mold or in the end of arm tooling, might actually deform this wall. So that's something that we want to consider during material selection and mold construction and automation construction. All right, the next part of the molding cell that the part would interact with is our vision systems. So this is, again, probably a typical thing that injection molders and manufacturing houses have. But one thing that I would highlight for our micro cells is we have inspection cameras and vision systems that inspect the parts a little bit post molding, but we also have what we call checker cameras that basically are just their sole purpose is to make sure that the part is actually there. A lot of the times our parts are so small that you really need a microscope to see them with any kind of detail at all. So if you were to look at the press from across the room, you might not necessarily, you wouldn't really be able to tell if the automation had a part or not. So one thing that is necessary for us to do is have the robot arm come into the molding cell, grab the part, exit the molding cell, and then immediately get photographed to make sure that the part is present and not stuck in the mold or haven't been influenced by static and flew off to oblivion or something like that. And these inspection cameras that we use, they have to be very precise because of how precise the parts are. So our acceptance or rejection criteria for checker cameras like this might actually go down to the resolution of the pixel within the software or on the screen. So we need to have technology like that. And some of our vision system nowadays are even instituting like machine learning or AI learning software so that they can, see what a good part is and then see another good part and then see a bad part and then get better at recognizing whether the part is present or not as time goes on. So we do have vision systems. The checker cameras just check to see if the part's present, and then an inspection camera will exist in the same cell to pretty much just look for gross defects, right? So if we have a sharp edge, like kind of depicted in this picture, like a dead sharp, right, we might inspect to make sure that there isn't some kind of micro no-fill there or something like that before the parts can get transported to metrology for more robust inspection. So speaking of that, how do we transport these parts and how do we collect them, right? So in some cases, your end of arm on the right side of the screen might be able to exit the molding cell, come over, reject a part in these chutes if it has to, or drop a part into these collection tubes. Hopefully we can get away with that. But sometimes we can't. An example where we couldn't might be that the part has a sharp edge, like in the last image, and has high rigidity in the material. So the very last thing we want to do is mold a successful part, have that part get presented to a checker camera, pass the checker camera, go to the inspection camera, pass the inspection camera, so everything's good to go, and then we drop it into a tube, and then the tube, it lands in the bottom of the tube, and then it dulls the sharp edge, and now the part's not good anymore. And we don't have any proof that it's good or bad anymore. That's one of the worst case scenarios. So we have to be very aware of that risk. And another risk might be if these tubes are, say, acrylic, which is polar, and we're molding also another polar material, the static that might build up in this cell might be worse than if it was a non-polar material, right? So not only is the polarity of your material important for static control, but also what is the polarity of the container, the vessel that it's going to be stored in or interface with. Those are the kinds of things that are going to dictate the static situation over time. And once the static gets bad, it can be difficult to combat. One thing that I haven't mentioned yet is, it might be obvious, is that we have anti-stat fans that are mounted pretty much everywhere in these cells. That's what this box is here. So going back to my scenario where we don't want to drop it into a tube because we don't want to dull a sharp edge, this is where more robust automation might come into play and alternative packaging might come into play. So I mentioned, you might remember at the beginning of the presentation, that we have a 6-axis capability. That's what is depicted here. And in this scenario, we might pick apart, say, with a vacuum instead of a pneumatic gripper, because we don't want to smash the part because of its rigidity and its delicate features. So we'll pull it with a 6-axis end of arm tool on a vacuum and then place it in these gel packs. So these gel packs are 10 by 10 grids that can hold 100 pieces in about a pack about this size, right? So more robust automation and alternative picking techniques can help pretty much eliminate all of those dangerous scenarios that I mentioned before. Right. And the last category I kind of want to talk about here is the metrology aspect of things. How do we inspect these parts and how do we handle them while we inspect them? And again, I have two specific things that I want to highlight. So sometimes the parts are so difficult to measure just because of how small they are. Maybe they have internal features. If you have an internal diameter that's maybe 10 or 15 thousandths, and then you have features inside of that can be difficult to see with the vision system or an optical measurement system. So in those scenarios, we actually utilize CT scanning. So I believe we are the only institution in Massachusetts that is not a medical healthcare facility that has CT scanning. And we use this to X-ray the parts. So we'll put the part in the CT scanner, close it, and that's good because now we don't have to interface with the part as much there's no non-contact measurement. And we'll X-ray the part and then compare that part to the SolidWorks file that the mold construction was based off of. And we can take our measurements that way. And this is great because we can even do robust things like GD&T, things that are kind of nebulous and more difficult to measure, especially if you're using an optical system this way. But there are some issues, like CT scanning can get kind of complicated if you have multiple densities in a part. Maybe it's two-part component or an overmolded component or something like that. And in those cases, a lot of the times we will have to resort to optical measurement systems. And the point that I want to make here, and it's my last point, is that I want to emphasize the precision that has to go into everything, again, that we do, right? It's calling back to that attention to detail that I mentioned before. So in conjunction with molds and end-of-arm tooling and all these other things, we also make inspection fixtures in our shop. And the one thing I want to highlight here is the tolerance stack up of everything that we make in the shop, including something as simple as this, right? So let's say we have a part and it has a 1,000th flatness spec on it, right? If this base plate has flatness within half a thousandths, and then these fixturing plates have another flatness of a half a thousandths, and then these mirrors are off by a few degrees. You see where I'm going with this? The tolerance stack up of this fixture might actually fail a good part. So we have to create something as simple as a fixture and then almost inspect those fixtures to make sure that they are as precise and robust as they possibly can be, because the criteria that we're inspecting to is so tight, right? So this, again, is that attention to detail in everything and anything that might not even be obvious to you. This is the difference between how to be successful and how to not be successful when it comes to micromolding, right? So with that all being said, I just kind of want to reflect back on the whole kind of overarching concept of what we've been talking about today, which is shouldering that responsibility to make sure that you have that level of precision in every single aspect of the program, right? And we consider this so important at MTD that we actually have pretty much built our entire business model around it, right? So at MTD, we have all these different categories: micromaterials expertise, part design, tool shops, molding, metrology, and even automation and packaging. And the reason why we do that is because we understand that the history of a part, the story of a program, and the attention to detail that's necessary through that life of an entire program is what makes us so good at what we do, right? So with that, thank you very much for listening, and I'd be happy to take any questions.
Can't hear you, John.
Hopefully I still got you guys on the line.
John, you muted. Oh. No, it doesn't work. Can you say something?
Yes, can you hear me now?
Ah, yeah, we
There
do.
you are. Yep.
Okay. Good. I will go ahead and get started with a couple questions here. I've seen a few come in, and keep sending those in as we move forward with this Q&A portion. First question, this is a good one. How does this apply to exotic materials like bioresorbables?
Right. Yeah, that's a good question. So that's something I didn't talk about at all in this talk, but bioabsorbables are, for those that don't know or may not know, they're materials that are implanted into the body, perform a function, and then degrade into compatible compounds, benign compounds most of the time. So that's a huge part of what we mold. And I think, everything that I said still applies to bioabsorbables, but the thing I would probably emphasize with things like that is the storage and handling of them, like the storage in particular, right? So those materials would be temperature controlled and humidity controlled pretty much all the time. So when we mold them, they're dried and blanketed with nitrogen. And then when we package them, we'll purge them, vacuum seal, nitrogen purge them, vacuum seal them in a foil bag so that they can't get penetrated by things like UV light, and then store and ship them usually on ice, right? So that's to prevent any early hydrolysis or degradation due to heat, right?
Okay, thank you, Patrick. I got another good one here. I think you're gonna like this one. What kind of tooling capabilities do you guys have in-house?
Yep. Yeah. So the machine shop that we have conventional CNC, obviously. We do wire EDM, we have sinker EDM, and we have our own isolated grinding room with its own ventilation. And then something called a Cerix, which I would encourage you to look that up if you don't know what it is, but it's basically a combination of, you might say, sinker and conventional CNC. So you would create a small electrode, and then the Cerix will cut the same way a CNC does, but with a single electrode. So we can make ultra small inserts and features utilizing that technology.
Interesting. I got another one here. Here's an interesting one. Can you use non-contact parts removal from machines such as vacuum, even if it's micro size? And if so, how?
Yeah. So sometimes, sometimes you can. It depends on a lot. It depends on if you have the surface area, enough surface area to purchase on the part, and then also on the vacuum. And then it depends on if you can design the end of arm kind of stack up to utilize enough vacuum, I guess, right? So if your orifice is only this small to pull a vacuum on, how do you get effective suction, right, to pick that with vacuum? So kind of the limitation is your own imagination there. Can you add multiple openings to interface with a runner system? Maybe for example, that's a good example where you wouldn't want to degate early, right? So that you could have more surface area to pull a vacuum on to demold the whole part out without getting it with grippers. That might be a good example, right? But again, it's possible, but it's on a case by case basis, and there's really no one shoe fits all for something like that. But we do it.
Okay, thank you. I got two kind of related questions here. What is the smallest subgate you have been successful with? And then off of that, what is the smallest diameter and the LD limit you would consider for stroke length max for ejector pins?
Yeah. Well, that's a good question too. That's a good question too. The tunnel gate, I would say, or the gate diameter, I don't know what's the smallest one that we've done, but it's measured in probably just a few thousandths. I don't know if you'd want to necessarily go smaller than that, not because it's not possible, but because of gate freeze time, right? So, like, minimizing the gate to minimize vestige or aesthetic things, that has diminishing returns after a while on the manufacturing side of things, because if we can only keep the gate open for a fraction of a second, we're going to lose cavity control over optimizing the part. So, we've gone, it's measured in thousands. I don't know off the top of my head what that is, but anything below that, and you'd be running a really, really fast gate freeze time. And in terms of the L over D ejection stroke thing, that I don't think I can answer right now. I'm not sure about that. That's a very good question, unfortunately.
Okay, well, thank you. I've also seen a couple of the same questions come in about showing up to this webinar a little bit late and asking if it was recorded. So this has been recorded from the beginning, and we will put it on our YouTube channel sometime either within the next week or so. So stay tuned for that. We'll probably be posting that as well. But here's the next question. What techniques, equipment, processes, and so on have you found most effective at dealing with static on tiny parts?
Mm-hmm. Yeah, so static. So if you can blanket everything with anti-stat fans, that's step one, I think. And then beyond that, I think your best shot at dealing with this, right? Because the ultimate goal with dealing with static is that you don't have to be there, right? Because ideally in injection molding, we want everything to run automatic and we want everything to run fast. So we have to invent some kind of way to create an automated scenario that can run over time and not have static buildup, right? So some things like, airflow and things like that, control that. That's step one. The two other things that I would suggest would be, the first one would be maybe, and this sounds kind of silly, but it can actually help, slap a grounding wire on your machine, or on the platen. See if you can intentionally ground some of the external static somewhere else. I've actually seen that make a huge difference, and it's really cheap and it's really fast and it's really easy. And the other thing I would say, and I harped on it a little bit during the presentation, but is if you do those things and you're still having an issue, start getting a little nerdy about it and looking at the polarity of all the things that are interfacing with the part, right? So the part material is whatever it is. So if it's a polar material, it's a polar material, and that's fine. But if you're trying to put it into an acrylic container, what if you can put it into a polyethylene container instead? Or what if you can put it into a container with foam in it, or something along those lines, right? To reduce the amount of, I guess you could call it ambient polarity, to try to control the cell once you're not there anymore. So those are probably my top three suggestions.
Thank you. Let's go to a couple more here. Here's the one that I think probably multiple people have in the audience. is, do you fabricate micro molded part tooling for outside customers to run in their own facilities?
Yeah, typically no. Typically no. Usually the model here is that, our customers would own their inserts, their part cavity, core and cavity inserts, but typically MTD owns all the mold bases that those inserts and stack ups run into. So typically no. But if you have a specific scenario, one thing I can tell you is that the leadership here is willing to listen to special scenarios. So, if you have a program that you think we might be able to help you with, it might not hurt to reach out and we'll listen to your story.
Okay, thank you. Another good one here. In molding, what is your machine range and are they all Sodics?
Yep. Yeah, pretty much all Sodics. So they're all 20-ton presses. And they're all V-line injection units. And we run pretty much 16 and 14 millimeter plungers. So that's it gives us, the same consistent footprint that we kind of exist in. But besides that, the only difference between the presses would be the verticals versus the horizontals, and how old they are. But it's basically all 20-ton. I think they're the GL line injection unit machines.
Okay, thank you. Let's go to the next one here. What special geometry considerations are necessary in subgate design to prevent gate flaking?
Okay. So that's a good question. It's kind of a combination of gating strategy and material strategy. So I think with that, like some of those auto D-gate geometries, you can find out there in the world the angle of approach that tunnel gate interfaces with the part. And subsequently how much steel is in between the runner system and the wall of the part. That angle and the amount of wall stock you have there actually is different depending on how ductile or brittle your part is. So I would say that if you're getting flaking like that, then maybe you have that angle wrong or something like that. Or maybe instead of taking that typical tunnel kind of cone shape, you can make it in maybe like a cashew shape. So a lot of those kinds of things can help be prevented with specifically changing like contact angle of that subgate.
Okay, thank you. We are getting close here to 2 o'clock, and we'll keep going with a couple more questions. There's a ton of them in here. So if Patrick, if you'll hang on a little bit and
Sure.
answer a few more for us. Otherwise, this will be recorded and posted on YouTube, as I mentioned before, so you can come back later if you need to. So just wanted to mention that as we get towards the end here. I'll move on to the next question. With regards to CT scanning these tiny parts, do you guys struggle with pixel size and image quality? That seems to be really challenging with CT scanning ultra small features.
Yeah. Yep, that's a good question, and we've seen that before. So resolution of CT scanning, I think I would say is probably the hardest challenge above density differences, like I mentioned, right? So if we overmold a steel pin with our technology, we're really only going to pick up the highest density material. So that's a limitation we have. But besides that, the resolution is kind of a problem. Yeah, it can be. So I think we can try different things like scan speeds and element size and things like that to try to zero in on that. But that sometimes is the reason why it would drive us to making a complex or like a high precision fixture and moving it to something optical or hopefully still non-contact measurement. But yeah, that's a good point. It is kind of a point of contention with CT sometimes.
Yeah, it makes sense. Okay, here's another good one. Is there or is the plate mold design commonly used in micromolding?
Yeah, 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 yeah. That's a pretty easy one, but yeah, it is. So I for the sake of time, I didn't talk about three plate techniques in this, believe it or not. But yes, if I had a little bit more time, I probably would have. But we do those fairly regularly, and they're totally possible.
Okay, thank you. Is it possible to have cavity sensors in micro parts? If so, what would you recommend?
Yeah, sort of, kind of. So cavity sensors, it's oftentimes impossible to get, like, say, a pre-gate and end of fill or post-gate and end of fill sensor in there, right? Like you might like to with RJG or something like that. Um, just because the parts don't have enough room. There's just not enough room to get the sensors in there. And even if there was, the pressure differential between gate to end of fill, or even the distance, might be, I don't know, 0.05 inches or something, so the pressure curves would pretty much look the same. Another way to say it is, like, sometimes it's difficult to say profile or something, because you just have to think profile like an ejection speed or something, because you just have to think about how much time you have, what window you have for opportunity to, like, utilize two different injection speeds, for example, right before the part's just full all of a sudden. So pressure sensors kind of suffer from the same thing, just because inherently the flow path isn't very long. So if you do want to get pressure sensors in there, you can still sometimes get them behind the head of an ejector pin, but you're not necessarily going to get, like, a pressure gate and then an end of fill or something like that. You'll just get a cavity pressure.
Okay, thank you. Let's go to a couple more here. A second. Do you run hot runner molds for micro parts?
Um, Not really, but we can. We can. So we run hot sprues from time to time, and we come pretty close to running hot runners before, but not necessarily. So there's a few things with hot runners and micro molding that I think sometimes it's the justification is applicable and sometimes it's not. One thing with hot runners is the compressible length of the shot increases, say, and in macro, that's not so much of a big deal. In case hot runners are usually oftentimes a better choice in macro, but in micro, you have, um, a lot of things going on because of how high your shear rate is and how fast your cooling rate is. So the distance, if you increase the distance between where you're controlling the velocity of the melt at the nozzle tip and then what it's doing in the end of the cavity, that can kind of get you it can kind of be hard to collect accurate data in terms of processing, if that makes any kind of sense. And then also with hot runners, because injection molding, the shot sizes are so small, the residence time is something that we have to be very wary of. And keeping the melt hotter for even longer, kind of increases the residence time and can add to some things like molecular weight loss if we have a super sensitive material like a bioabsorbable or something. So we have done it before. We've done hot sprues before, and we've come pretty close to hot runners. And I wouldn't say that we'll never do it, but typically they're all cold.
Okay. Thank you for that. Another good one here. What is usual min-max mold cavitation and what are the usual cycle times?
Well, uh, cycle times vary all over the place. Because sometimes, they can be tens of seconds if we're talking about a hand load overmolding job, or it can be, just a few seconds overall if it's super automated. So the cycle time, I think I could tell you that we don't really have a typical cycle time because you know, everything that we do is just so varied. We pretty much mold every type of plastic we can in every type of corner of med device that we can. So the cycle times are kind of everywhere. But the cavitation, believe it or not, most of the molds are single cavities. And we've gone up to maybe 4. You know, I say 1 to 4 is probably the most common. We've ventured out of that space a little bit from time to time, but things can get challenging when you get to super high cavitation because, you know, shear imbalances get crazy because the shear rates are exponentially higher in micro. So your fill behavior when you get to super high cavitation starts to get feel a little bit out of control sometimes. I don't want to get too much in the weeds on why that is, but if you watch I'm pretty sure it's in the last Sodic presentation I did, something called the second Newtonian plateau, that the longer we increase the flow length of parts that are exposed to shear, ultra high shear exposures, the less non-Newtonian plastics start to act. So controlling 8, 16 cavities or something can be really kind of difficult sometimes, especially if we have, you know, we're measuring to the thousandths on flash or something like that, right? So we like to keep the cavitation low so that we can keep control of the parts. And then the other part is shot capacity, barrel capacity, right? And if we get to a 16 or a 32 cavity mold, you know, the projected area and the barrel capacity for what we're set up to do might just end up being too high.
Yeah.
Thank you. Thank you. I think I got one more good one here and we'll wrap it up. How do you check the melt temperature of the material?
Well, the melt temp of the material is we pretty much just monitor it through the machine, right? We set the melt temps and then we'll set upper and lower limits to that, and then monitor, we'll monitor that through the process. But rarely, I've done it sometimes when there's been a problem. We'll use, I guess, like laser probe or whatever they're called. I don't know, I forget what they call it right now, but like pyrometers that use lasers. And we'll check purge that way to see what the actual melt temp is, and if it matches what our set points and our actual readouts are. So we'll use laser pyrometers if we have to. I've done that before, like with parts that have excessive stringing. They have excessive stringing, and that can be causing all kinds of issues. And we'll go, okay, is the nozzle what the nozzle says it is? And in those cases, we'll use non-contact pyrometers to do that. But usually we don't have to do that, and we can just monitor it through the machine output.
Okay, well, thank you very much. I think that's gonna wrap it up for this webinar. Again, thank you for supporting our Sodic and Friends platform here. And we hope to see you in the next one. We were going to continue to do these throughout the year. We have another one coming up in a couple weeks with Syensco, a material manufacturer. And yeah, like I said previously, this will be posted on YouTube, so feel free to come back and revisit, as well as watch past Sodic and Friends webinars there as well. Kohei, if you have anything else.
Yeah, Patrick, thank you. I enjoy your presentation, sharing knowledge to the community. This is fascinating to not just molding, but after the process, which is very, very educational. Thank you.
Yeah, absolutely. Thank you.
And those who haven't been answered, we're going to share the Q&A with the Patrick and MTD group. So you may get the answer directly from my MTD group. So we share all the Q&A with them. So in case you are thinking that been answered, you may have some answer from him direct.
Sure.
Perfect. Thank you.
All right. Thank you.
Yeah. Thank you very much. Hope you enjoy.
Bye.
Bye-bye.